continue with the Fibonacci sequence for a few minutes and let's look at some more results. Okay. Lemma. For any n greater than or equal to 1, for n greater than or equal to 1, f of n and f of n plus 1 are relatively prime. Relatively prime. Proof by induction. By induction. Okay. Base case n is equal to 1. Well, for n is equal to 1, f of 1 is equal to 1, f of 2 is equal to 1, and 1 and 1 are relatively prime. So f1 and f2 are relatively prime. Okay, so now assume that induction step assume true for n is equal to k, show for n is equal to k plus 1, right? So I am going to assume it's true for n is equal to k. We want to show for n is equal to k plus 1. I'm going to assume the contradiction. Suppose there exists x such that x divides f of k plus 1 and x divides f of k plus 2, right? Then if f divides f of k plus 1 and f divides k plus 2, then x divides f of k plus 2 minus f of k plus 1. If x divides a, x divides b, then x divides a plus b, x divides a, x divides b, then x divides a plus minus b. Oops. Plus or minus b. Okay. Great. But f of k plus 2 minus f of k plus 1 is exactly equal to f of k. Therefore, x divides f of k, right? As f of k plus f of k plus 1 is equal to f of k plus 2. Well, therefore, x divides f of k and x divides f of k plus 1. But by assumption, f of k and f of k plus 1 are coprime. But f of k and f of k plus 1 are coprime. Therefore, x has to be equal to 1. Okay? And therefore, f of k plus 1 and f of k plus 2 are coprime, and therefore f of n and f of n plus 1 are coprime for every n greater than or equal to 1 by induction. Okay, great. Now, here's a slightly more fun result that's not just direct computation, more or less. Lemma. Let me denote f r comma s is equal to fr times fs plus fr plus 1 times fs plus 1. Okay, then frs is equal to then frs only depends on r plus s. Okay, so it doesn't matter what exactly r and s are, it only matters what their sum is. Proof: we will show f rs is equal to f r minus 1 s plus 1, and then f rs is equal to f of 0 comma r plus s. Okay, and so it basically depends only on r plus s, right? Here's the proof. Oops. Well, fr times fs plus fr plus 1 times fs plus 1 is equal to, well, I am going to write this as, I'm going to write fr as, I'm sorry, fr plus 1 as fr times fs plus fr plus fr minus 1 times fs plus 1 is equal to fr times fs plus fr times fs plus 1 plus fr minus 1 times fs plus 1, which is exactly equal to fr times fs plus fs plus 1 plus fr minus 1 times fs plus 1, which is fr times fs plus 2 plus fr minus 1 times fs plus 1, which is exactly equal to f of r minus 1 s plus 1, right? And so if I repeatedly do this, it's going to give me that fr minus fr comma s is equal to f0 comma fr plus s, which gives me corollary for r comma s greater than or equal to 0, fr into fs, so fr comma s is equal to fr into fs plus fr plus 1 into fs plus 1 is exactly equal to f of r plus s plus 1, right? And the proof is relatively simple. Proof f of r comma s, I have said that this is equal to f of 0 comma r plus s. Well, this is by definition f of 0 into f of r plus s plus f of 1 into f of r plus s plus 1 is equal to 0 times f of r plus s plus 1 times f of r plus s plus 1, which is equal to f of r plus s plus 1, right? And so I have a relation between two very different r plus s. Doesn't matter what fr and fs are, I can always relate all of them to f of what exactly R and S are, all of them are always related to FR plus S plus 1. Okay. And so I will show that lemma given any integer, given any integer x such that x divides, if x divides any two, at least two of fr, fs, fr plus s, then f divides all three of them. Then f divides all three. Okay. Proof. Suppose suppose x divides fr and x divides fs. Then x divides fr times f of s minus 1 plus f of r minus 1 times f of s, right? But that is exactly equal to, therefore, x divides f of r plus s, right? Because this is equal to f of r comma r plus s minus 1 comma 0, right? Which is exactly equal to f of r plus s. Now suppose instead it divides, suppose x divides fr and x divides fr plus s, right? But then by the same exact logic, so by this, x divides fr minus 1 times fs, right? But fr minus 1 and fr are coprime by my previous lemma, and therefore x has to divide fs unless x is equal to 1, in which case it anyway divides fs, right? Similarly, if if x divides fs and x divides fr plus s, then x divides fr times fs minus 1, which implies x divides fr, and hence I have my lemma. Okay, so these are some examples related to what do you call Fibonacci sequence. We'll stop this here and we'll start section 7.2.